Thank you, Jacob. So it's great to be here 2 years after we co-founded this conference, and I really hope that next year it will be non-virtual again. I'm the chief data scientist of the Intel's internal AI group, and I'll talk today about AI innovations and their applications at Intel. I'll start by a brief background about AI at Intel. I'll continue with talking about the key recent AI innovations, and then give some examples for applying AI innovations internally at Intel. Well, Intel is well known as a hardware company, but AI is taking increasingly central roles in the company in the recent years. One role is providing hardware and software for AI. We provide hardware and software both for classical machine learning and for deep learning. And you probably heard about the recent release of the Habana Gaudi accelerator, but of course, there are many other activities and products that are either released or going to be released. Another role is using AI to make smart products. So you're probably familiar with Mobileye that uses AI for making the car smart, but we're also using AI embedded into our processors to make them more efficient, improve power and performance. And last but not least, we use AI to transform our own operations, analyzing the images, text, time series, tables that are generated by Intel's internal operations to create value for the company, making our operations more efficient and improving our products. And a lot of this is done or even led from Israel. Now zooming in on our group, the Intel IT AI group, is the internal artificial intelligence group. Our main mission is to transform and upgrade Intel's internal work using AI. Our group exists for 12 years, has over 200 professionals, most of them in Israel, deployed hundreds of solutions to production today, and brings annual value of over $1 billion every year. You can see here the verticals that we are active in. So I mentioned processor architecture, making the products adaptive for boosting power and performance by adapting to the usage. You may have heard this year about the Gen 12 processors that have the thread director embedded into them. So the AI model of that thread director was developed in our group. We're also active in design and validation, making manufacturing adaptive, personalizing processor production. Instead of generating each processor the same way, we consider the history of each processor, and also helping with sales, which I'll touch upon later. Overall, the AI models influence almost every processor, every product that Intel provides. Most of this cannot be published because these are Intel secrets, but some of this can be published, and I'll give some examples today. So I said that I'll talk about AI innovations, and of course, main question is, what are the key recent AI innovations in AI? And there can be various perspectives about that. One perspective is looking at the key recent AI applications that made breakthroughs, or the key new developments in AI applications. And I listed here 5 that I think are most significant. So one application area of AI that made tremendous breakthroughs is obviously language models. GPT-3, Jurassic, they don't just be the state of the art in some of the NLP tasks, but they are also able to get instructions and do a variety of different NLP tasks, which makes us think that it's a step towards AI that understands. Of course, autonomous driving has a lot of progress in the recent years, and you can see, for example, the movie on YouTube, Autonomous New York, recently released by Mobileye, seeing how the car autonomously navigates in the crowded city of New York. Amazing breakthroughs in biology, AlphaFold 2, predicting protein folding. That's really amazing using graph neural networks. A lot of progress in machine programming, coding based on AI. You can consider, for example, the GitHub Copilot, the recent Alpha code, and these use both language models and graph neural networks in some cases. And also the AI chip designer using AI to design chips. Some of this was also published in various papers. So this is one way to look at what are the main innovations in the recent years. Another way to look at it is to take a step deeper and try to think about what are the key techniques that evolved in the recent years that enable these innovations. So I listed here several techniques that made significant progress in the recent years. They are not necessarily new. For example, self-supervision transformers enable the language models, and graph neural networks enable the AlphaFold 2 and many of the machine programming applications. And deep learning for tabular data is just emerging, but it's also very important because it's going to handle a large portion of the market, which uses tabular data. That's a large portion of the AI problems. And there are many other techniques here as well. So at Intel, of course, we either use or experiment with or develop most of the techniques that you see here, and also most of the applications that you have on the previous page, like language models and machine programming and so on. But I would like to focus today just on one example, one area of innovation that I think is important, and tell you a little about how we implement that. And the area is supervision without labels, self-supervision and weak supervision. I'll start by telling you a little about it and why it's important, and then I'll tell you how we implement it. So the most common learning paradigm in the industry is supervised learning. This is also the first thing that you learn in university usually. And this learning paradigm assumes that you have a kind of ideal scenario in which you have labeled data sets where you have lots of raw data that can be labeled. And often you have pre-trained models that can be adapted to a new problem using just a few labels if you don't have a lot. And then it's just in a click of a button, you just train your model and get a solution to a problem. But the case in reality is that usually this is not the situation. So in many use cases, we don't have labeled data. The labeling by experts is very expensive. There's imbalanced data. We don't have the positive examples to label. The minority classes are very rare. And the use case is domain specific, so we cannot use pre-trained models. So this is the need for labels, for reliable labels, is kind of a glass ceiling for AI. And recently, there are attempts to break it. And one such attempt is using self-supervision, which means using the unlabeled data to create some labeling that can be learned. So an obvious example is the example of language models that just take text, hide some of the words, and use the missing words as the labels that need to be learned. So you see here, for example, that I hid some of the words, and the language model is learning them according to the context, using them as labels. Another type of self-supervision is contrastive learning. You see here the images, so we can do label-preserving transformations of images, for example, rotating the cat and the watch and so on, and learning from image pairs. The information that is learned is whether a pair of images originates from the same original image or not. And it turns out that just learning this is very powerful and can be even further strengthened by semi-supervised learning. After you learn that, you add a little label data and fine-tune that model, and it has great power. And of course, there are additional types of learning. Currently, non-contrastive learning that only uses the positive examples is gaining popularity. So self-supervised learning is a really promising approach for overcoming the need for labeled data. And somewhere in the middle, we have weak supervision between supervised learning and self-supervised learning. Weak supervision is not new, but again, it has several new innovations in the recent years, and it means that we learn from labels that are partially correct or have some uncertainty. The uncertainty can be stochastic, as in this example. There's some probability for the correctness of the labels. We might not know it. It can be another type of uncertainty is multiple instance learning. we learn from labels that refer to sets of samples instead of single samples. So we know that at least one sample in the set has this label, but we don't know which one and how many. We know that there is some red sample, but we don't know if there's just one and how many are red and which one is red. And also the classical approach of active learning is relevant here, iterative and requesting labels for additional samples. So this is a reminder or an introduction for those who don't know it about self-supervision and wing supervision. And we apply these various methods at Intel, and I'll give one or two examples for that. One example is related to AI, using AI for sales. As I mentioned, this is one of the verticals that we are active in. Intel is selling B2B. We sell to big customers, to companies that have not necessarily big, that use our processors to build computers and other machines. And they usually enlist into our partners program, and we have lots of information about them, the websites, the social media, the Twitter accounts. We can collect news about them, sales data, and so on. And we use all this data and crunch it using AI to provide two types of outputs. One of them is product recommendations, and the other is sales assists, alerting whether this company now has a new investment or has some new domain that it enters or launches a new product. And that's a reason to contact it and offer it new things. And this goes either to salespeople who for covered accounts or for bots for accounts that are not covered. We have lots of customers, so not all of them are covered by people. How is it related? How is this related to weak supervision? So many of the tasks that we have to do for supporting Intel sales involve unlabeled data, which is difficult to label. Think, for example, about identifying tweets that would interest Intel salespeople. How can you find a tweet about some partnership of an Intel customer or some product launch or some merger and acquisition? That's like a needle in a haystack, right? There are many tweets. How can you identify the important ones? Characterizing partners based on the websites is also difficult. You have many websites, they don't have any labels. How can you identify what's the market segment of the company, the product type? You can do some manual labeling, but it's very tedious, and we have like lots and lots of customers, right? That's very, very difficult. The approach we took is a weak supervision approach, and for these use cases, we used a tool called Snorkel. This is a tool that enables weak labeling based on rules, and it was developed by the Stanford AI lab. We worked with them to improve and extend it, and eventually published a joint paper about our work. By the way, they later founded a startup around Snorkel that a few months ago became a unicorn. This is a schematic from our paper about how it works. So I'll just walk you through it in kind of an overview. So let's say we want to identify tweets, whether a tweet is important or not, relevant for Intel salespeople or not. So we have a domain expert that provides some rules, like if the tweet contains partners, then maybe it's good. If it contains aha or emojis, then maybe it's bad. We translate these rules into Python code. That's easy. And now we can just do the wisdom of the masses and see for each tweet if most rules say that it's good or not. But the problem is the Hertz phenomenon. These rules are correlated. So we use a generative model that tries to cancel out these correlations and provide actual probabilities based on the rules to the various tweets. Now, the second part is using an AI model to learn these probabilities using a neural network. And then the neural network kind of generalizes these rules. Eventually, the answer is an ensemble of the rule-based model based on the human knowledge and the AI model. And we also use the rules for some rebalancing of the input. You can have all the details in the paper. So this is an example where we started without any labels, and still we managed to build something that really finds interesting tweets. And of course, we evaluated it based on a small set of tweets that we had, which were labeled. So this system was deployed in production and became useful, and we also deployed the web characterization system recently, and you can read more details about this in the papers that I mentioned here. Another example for using weak supervision is for a completely different story, validating Intel's graphics. So when we update the drivers of Intel's graphics, we need to test that when you play videos and games on that processors, they look good. This is tested on many systems, and the last stage is random. You don't have a reference, just playing random videos and random playing computer games, and the response of the game can also be random. And you can see here some illustrations for corruptions that may happen in the images. Sometimes it's more subtle to detect. Sometimes it's difficult to distinguish it from good images. Sometimes it's easier. And the images at the bottom look okay, but they also represent a corruption, because if you look at them from left to right, it actually represents a sequence of images that has some flicker that are corrupted. I want to go into more details of the problem. I'll just say that we provided a deep learning-based system for detecting these visual corruptions in videos, and we used manually labeled videos that were generated with driver bugs and had labels per frame manually generated. And of course, it is tedious to manually label each frame. And later on, we found out that we can use here weak supervision, so we can train based on labels per video segment or per video rather than per frame. We know that there is some bad frame in the segment or in the video, but we don't know which. And it turns out that in many cases, if we have enough cases of bad frames in the training data, this could be good enough for many applications. So this saves manual labeling per frame while providing better results than an unsupervised model. Not as good as a supervised model, but still in many cases good enough. And again, this was deployed on dozens of machines. You can have some picture here, and it is used at Intel for the last couple of years. And you can also read about it in our papers in Europe's workshops and in this year's KDD conference. Okay, so I gave some examples for text and for image. What about tabular data? How does it fit in all this party of using deep learning and advanced methods? And can deep learning outperform classical machine learning in classification and regression for tabular data? I won't have time to talk about all of this, but luckily later today, my colleague, Dr. Aviv Schwartz-Ziv from my team, will talk about it based on our recent paper in the Information Fusion Journal. Tabular data, deep learning is not all you need. Since then, there were more advances in tabular data, and Ravid will also mention that, I think. And I mainly talked about use cases that are not related to increasing hardware performance. I said that this is more sensitive, but we cannot share a lot about it. But still, how does AI improve your computer? What can we say about that? So I won't have time to talk about it today, but tomorrow you're welcome to join Avishai Wagner from our group, who will tell everything we can about how we use AI to increase hardware performance. I have just a few more notes about what we do to promote and adopt AI innovation at Intel. The key thing is what you see at the bottom, at the top left, hiring data scientists that either hold or pursue advanced degrees in the field, really strong data scientists. And we also do lots of other activities, participate, presenting conferences, investing in trainings, in academic collaboration, and so on, to make sure we are at the front of the innovation in the field. More details about our use cases can be found at the Intel IT site. And if you are interested in more details or in the open positions that we have, then of course you're welcome to contact me. Here is my email. Thank you.
Thank you. Thank you very much, Dr. Amitai. Marvelous talk. We have a few questions for you. So let me start with the first question. Does Intel support reinforcement learning in their edge chip?
Okay, so of course, reinforcement learning can be done in different ways. There are many algorithms for reinforcement learning. And we also have several offerings for the edge devices. The general answer is yes. And the best way to do it depends on the use case. And of course, you are welcome to contact me directly, and I can try to advise what's the best way to do it.
Okay, excellent. You touched a few times during your presentation about your researchers. All of us in the industry are trying and suffering from the same problem to hire the best talent in the area of AI. And for that, we also have a question for you. In your talk, you explained that you have over 200 people. We would like to ask you, what are their professional profiles? Are all of them data scientists? And if someone from our audience are interesting to be part of your amazing group, what he should do?
Great question. So about a third of our 200 people are data scientists, as I mentioned, people with, we call them applied AI researchers, people with advanced degrees or students for advanced degrees in the field. Other people are what we call machine learning engineers, developers of the environments and platforms that we use for machine learning. The data scientists focus on the modeling, the machine learning engineers focus on the platforms that we use for deploying the models, getting the data, monitoring the models in production, and so on. And we also have product people that work with our customers, learn the requirements, manage the projects, and help the projects succeed. If you are, any excellent student or graduate or expert in AI is welcome to contact me. We have lots of positions for each of these job type, job profiles. For data science, we require advanced degrees or being student for advanced degree for student positions. But for the other positions, a bachelor's degree, a relevant bachelor's degree could also be relevant. So you're all welcome to contact me. You have my email, and I'm also accessible via LinkedIn. So yeah, we are happy to hire. We keep growing all the time.
So we have another question to you, Dr. Amitai, which is going to be a little bit challenging based on what you are hearing now. And I'm quoting, okay? I heard Intel supports diversity and inclusion. Why do you hire only MCNs and PhD researchers? Can first degree graduate become a data scientist at Intel?
The answer is yes. So typically we hire masters and PhD experience, people with masters and PhD experience, because we need the research experience for being an applied AI researcher. But we do have some people with equivalent experience that don't have the masters or PhD. And if if you have this as a candidate, then of course you will be considered, and you're welcome to contact me as well. As I said, for other positions of product and machine learning engineering, there are different requirements.
Thank you. And the last question before we move to Dr. Moni Shachar. How do you balance between cutting-edge innovation work and deployment of hundreds of models to production?
That's a great question. So the main answer is automation. We have great platforms that our engineers built that do the production deployment and monitoring and data monitoring and all of that. And our researchers can focus on doing new things, breakthrough technologies that just leverage innovation to bring value to it.